When the James Webb Space Telescope first opened its golden mirrors to the cosmos, astronomers braced themselves for answers to questions that had lingered for generations. What they didn't expect was the scale of shock that followed. Webb didn't simply refine our understanding, it dismantled it. Galaxies appeared where they shouldn't, black holes grew faster than physics allows, and alien worlds displayed weather so bizarre it bordered on the impossible. Instead of offering a neat story of cosmic evolution, Webb revealed a universe more untamed, unpredictable, and awe-inspiring than we ever dared to imagine. Among Webb's most shocking discoveries was the revelation of what astronomers now call jumbos, pairs of Jupiter-sized worlds drifting together through the vastness of space, with no parent star to anchor them. For as long as we've studied planets, our understanding has been framed by the idea that planets are born in the cradles of stars. They take shape within swirling disks of gas and dust, feeding on the material around them, slowly assembling into bodies that orbit their stellar hosts. Yet here was something so profoundly unsettling that it challenged that framework at its core. Giant worlds, massive enough to rival Jupiter, existing not as solitary drifters, but as bound pairs, free-floating through the interstellar night. Their very existence raises a storm of questions. How could such colossal objects form without the stabilizing presence of a star? How can two of them remain gravitationally bound in the emptiness of space, a place where encounters are rare and gravitational interactions are fleeting? It is not simply the fact that they exist. It is the fact that they exist together that has left scientists struggling for answers. Webb's sharp infrared vision revealed these planetary duos in the Orion Nebula, one of the closest stellar nurseries to Earth, and a place astronomers have studied for centuries. Yet never before had any telescope shown us this. Each pair appears to wander the nebula with no star in sight, as if the cosmos itself had tossed them into the void after their birth. Theories sprang up almost immediately. Perhaps they were born around stars, but were violently ejected during chaotic gravitational interactions, flung into interstellar space, but somehow retaining one another's embrace. Or maybe they formed independently, not as planets at all, but as failed stars, objects too small to ignite nuclear fusion, but large enough to mimic the bulk of a gas giant. The problem with these theories is that none fits perfectly. If they were ejected planets, why do we see so many of them? Enough to suggest this is not a rare accident, but a common occurrence. If they are failed stars, why do they appear in pairs, moving in such unlikely harmony? The gravitational bond between two drifting worlds is fragile. To remain together in the violent environment of a stellar nursery, without being torn apart by the tidal forces of larger stars and the pull of other massive objects, suggests that there is something about their origin we do not yet understand. Some scientists propose that we are witnessing an entirely new class of celestial object, a hybrid that blurs the lines between stars and planets. These jumbos may represent a mode of formation that defies the categories we've relied on for decades. They are neither neatly planets nor neatly stars. They are something else, something that forces us to reconsider the boundaries of cosmic classification. What makes them even more fascinating is what they might reveal about the abundance of planets in the universe. For decades, we assumed planets formed only within star systems, meaning the number of potential planets could be estimated based on the number of stars. But Webb's discovery of dozens of jumbos suggests that the universe may be filled with far more planets than we ever counted. They may be hiding in the darkness between stars, drifting unseen, perhaps even outnumbering the stars themselves. That realization alone expands the scale of planetary diversity to an almost incomprehensible level. Imagine a universe not dominated by the stars that light it, but by countless invisible worlds that roam in shadow. Even stranger is what such worlds might mean for the possibility of life. At first glance, A starless planet seems hopeless, an eternal ice ball in the dark. But if jumbos are as massive as Jupiter, they could retain internal heat left over from their formation, or even generate warmth through the slow compression of their dense cores. In theory, subsurface oceans beneath thick ice shells could remain liquid for billions of years, powered not by starlight, but by internal energy. If such worlds exist in vast numbers, then the potential habitats for life across the cosmos might be far greater than anyone imagined. Life may not require a star at all. It may simply require a stable world with enough energy to sustain chemistry in the dark. If the discovery of wandering planet twins was a shock to planetary science, then what Webb revealed on the scale of galaxies was nothing short of cosmic chaos. Among its earliest and most jaw-dropping images was the sight of not 2, not 3, but 5 entire galaxies colliding in an ancient cosmic pileup, their vast star systems smashing together in a violent dance less than 1 billion years after the Big Bang. This was not supposed to happen so soon in cosmic history. According to our best models, the young universe was still a place where galaxies were small, irregular, and just beginning to assemble themselves from clumps of stars and gas. Giant, organized structures, let alone multiple of them crashing together, should have taken far longer to appear. Yet Webb's eyes revealed otherwise. In this stunning image, we see gravity pulling trillions of stars across intergalactic space, twisting them into arcs and filaments, blending entire galaxies into one sprawling, glowing battlefield of cosmic evolution. The sheer violence of such a collision is difficult to comprehend. Each galaxy involved in this event holds hundreds of billions of stars, countless nebulae, and supermassive black holes at their cores. When galaxies collide, stars themselves rarely hit each other directly. Space is vast. But their gravitational fields warp and tear at one another, stripping gas and dust into enormous tidal tails that stretch across light years. These streams then collapse into new waves of star formation, igniting thousands of fresh suns in brilliant bursts of light. Webb's infrared gaze pierced through the dusty chaos, capturing the fireworks of stellar nurseries being born in the wreckage. What we are witnessing is not simply destruction, but creation on an epic scale. Galaxies cannibalizing one another to give rise to entirely new forms, new shapes, and possibly even new homes for life in the distant future. What makes this even more astonishing is the time in which it occurred. Less than 1 billion years after the Big Bang, the universe was still young, still forming its first large structures. The prevailing theories had long held that such massive collisions were events of middle age, the kind of thing that happened after galaxies had centuries of millions of years to grow and gather mass. Yet here was direct evidence that the universe wasted no time in staging these colossal encounters. It forces scientists to rethink how fast galaxies grew, how quickly matter condensed into organized systems, and how chaotic those early times must have been. If 5 galaxies could come together so soon, then the early cosmos was far less stable than we once believed. At the heart of this crash lies another enigma: the fate of the black holes within these galaxies. Every large galaxy we know harbors a supermassive black hole at its core, often millions or billions of times the mass of our Sun. When galaxies merge, these black holes are pulled inexorably toward each other, spiraling closer and closer in a gravitational dance that can end in titanic mergers. Such events would unleash unimaginable energy in the form of gravitational waves, ripples in the fabric of space-time itself, propagating across the universe like cosmic earthquakes. Though Webb cannot directly detect these waves, the fact that we see a 5-way collision suggests that somewhere in the depths of this chaos, black holes are colliding, merging, and sending echoes through space-time that observatories like LIGO and future detectors may one day capture. This means Webb is not just showing us a picture. It's pointing us to an event that reverberates across the very structure of reality. And yet, for all the violence, the image Webb captured is breathtaking in its beauty. The galaxies stretch and swirl, their shapes distorted into elegant arcs, glowing with the light of countless stars. It is a portrait of destruction, yes, but also one of transformation. Over billions of years, this cluster of colliding galaxies will eventually settle into a single massive elliptical galaxy, its history written in the streams of stars and gas it once stole from its companions. Such elliptical giants are among the most common galaxies we see in the present-day universe, which means that what Webb observed may be the very process by which they are born. To witness it happening so early is to peer into the furnace where the largest structures in the universe were forged. The discovery also underscores a humbling truth. Collisions are not rare accidents, but fundamental drivers of cosmic evolution. Our own Milky Way is destined to collide with the Andromeda Galaxy in about 4 billion years, and that too will reshape both galaxies into a new form. Webb's snapshot of a five-way crash is, in many ways, a glimpse of our future. It tells us that galaxies are not static, peaceful islands of stars, but restless travelers whose paths inevitably cross, leaving behind legacies written in starlight. And if such collisions were already happening less than 1 billion years after the beginning, then perhaps the very structure of the universe has always been one of upheaval and transformation. To think of 5 galaxies, 5 colossal systems, each containing countless stars, nebulae, planets, and possibly civilizations, being thrown together in such a turbulent embrace is staggering. Somewhere in those galaxies, stars were being born, as others were being ripped apart. Worlds that once orbited peacefully around their suns may have been cast adrift or swallowed into new stellar systems. Entire cosmic histories may have been erased, while others were just beginning to unfold. It is a reminder of how fragile cosmic order truly is, and how in the grand scheme of things, chaos is the engine that drives creation. What makes Webb's revelations even more astonishing is that they did not stop at chaotic galactic crashes or rogue planetary wanderers. Just when astronomers thought they had mapped the limits of what earlier telescopes like Hubble could see, Webb unveiled something even more unsettling: galaxies that had been completely invisible to Hubble's eyes. These so-called Hubble dark galaxies emerged from the shadows under Webb's infrared vision, lurking behind thick curtains of cosmic dust, and they were not faint, quiet systems barely holding themselves together. They were bursting with furious waves of star formation. The fact that they remained hidden for decades of observation underscores just how incomplete our picture of the universe has been, and how easily its greatest engines of creation can elude us. The key lies in Webb's infrared capabilities. Unlike Hubble, which peers primarily in visible and ultraviolet light, Webb was designed to detect the longer, redder wavelengths of the spectrum, the very kind of light that can pass through dust. For years, astronomers assumed that if Hubble could not see these galaxies, they either did not exist or were too insignificant to matter. But Webb proved otherwise. The galaxies were not absent, they were cloaked, their light smothered by vast reservoirs of interstellar dust. Far from being insignificant, these galaxies were among the most active star factories in the young universe, churning out newborn suns at rates that defied expectations. In many ways, they are the hidden engines of cosmic growth, the places where the universe was assembling its first generations of stars in secret. The discovery of Hubble dark galaxies forces us to confront how biased our earlier picture of cosmic history was. For decades, the narrative went like this. After the Big Bang, matter slowly coalesced into galaxies, stars formed gradually, and the universe brightened step by step. Hubble gave us much of this story, But Webb showed us that it was incomplete. Entire populations of galaxies hidden behind veils of dust were actively shaping the early cosmos, and without Webb's vision, we would never have known they were there. This realization means that much of what we believed about the timeline of cosmic evolution must be revised. The early universe was not just alive with light, it was far busier, messier, and more prolific than we had ever suspected. Even more intriguing is the role dust itself plays in this story. Dust may seem like a nuisance that blocks light, but it is also a vital ingredient in the birth of stars and planets. These Hubble dark galaxies are rich in dust because they are rich in life's building blocks: carbon, oxygen, silicon, elements forged in earlier generations of stars and now recycled into new ones. To find so much dust so early implies that the universe's first stars lived and died much more quickly than expected, seeding their galaxies with the raw materials of creation almost immediately. Webb is, in effect, watching the cosmos rapidly enrich itself, as if impatient to set the stage for planets and eventually life. The sheer abundance of these hidden galaxies has stunned astronomers. Webb has not just revealed one or two, it has uncovered dozens, perhaps hundreds, scattered across its deep fields. Their combined contribution to cosmic history may be immense. If they were producing stars at such furious rates, they may have been major players in an event known as cosmic rionization, the period when the universe transitioned from being opaque and filled with neutral hydrogen to being transparent and lit by starlight. Until Webb, the drivers of rionization were a mystery. Now, these dust-shrouded galaxies stand as prime suspects, quietly reshaping the cosmic landscape while hiding from view. While hidden galaxies were emerging from the shadows, Webb also turned its gaze towards some of the most enigmatic and terrifying objects in the universe: supermassive black holes. For decades, astronomers had accepted that these cosmic giants, millions or even billions of times the mass of our Sun, took billions of years to grow. The prevailing wisdom suggested that they formed gradually, fed by infalling gas and collisions with other black holes, slowly climbing toward the colossal masses we observe today. Webb, however, shattered that assumption with observations that forced scientists to confront a chilling possibility. Some black holes grew enormous astonishingly fast, appearing in the universe's infancy less than 1 billion years after the Big Bang. These monster black holes are not just rare anomalies, they appear more common than our models would predict, and their existence strains the limits of current physics. The earliest universe was a chaotic place, filled with clumps of gas and dark matter, slowly assembling into the first stars and galaxies. In this environment, the birth of a supermassive black hole seemed almost miraculous. The traditional route, where smaller stellar black holes gradually accrete mass over millions of years, simply doesn't allow enough time to reach billions of solar masses in under 1 billion years. Webb's infrared precision, however, revealed the unmistakable signatures of these cosmic behemoths, their immense gravitational influence distorting the light from nearby stars and gas. Some of these black holes shine as quasars, blazing with energy as they pull in surrounding matter at incredible rates. The intensity of their radiation alone confirms that they are growing at speeds far faster than any conventional theory allows, challenging the very frameworks used to understand galaxy formation and evolution. What makes these discoveries even more remarkable is their scale. Observations by Webb suggest that some early quasars, the visible active manifestations of supermassive black holes, possess masses exceeding 1 billion suns. That is almost inconceivable in a universe that was still in its toddler years. The existence of such objects implies either a radical acceleration in black hole formation or alternative mechanisms that scientists are only beginning to theorize. Some models now propose that Direct collapse black holes may form when massive clouds of gas collapse under their own gravity without first forming stars, skipping several stages of the traditional growth process. Others speculate that mergers of numerous smaller black holes or super-efficient accretion fueled their rapid expansion. Regardless of the mechanism, these monster black holes force us to rethink the timeline of cosmic evolution entirely. Their presence also raises profound questions about the galaxies that host them. Supermassive black holes are intimately connected to the galaxies surrounding them, influencing star formation and the dynamics of galactic cores. If these monsters existed so early, the galaxies housing them must have grown quickly as well, assembling vast amounts of gas and dust under extreme conditions. Yet, the universe at that time was still forming its basic structures. So how could these galaxies have gathered enough material to feed these behemoths? Webb's observations suggest that the early universe was far more efficient at concentrating matter than previously thought, capable of producing not just stars, but entire galactic ecosystems dominated by black holes in a fraction of the expected time. The energy emitted by these early supermassive black holes is staggering. As matter falls into the event horizon, it is heated to millions of degrees, producing intense radiation across the spectrum. Some quasars shine with the brightness of 1 trillion suns, visible across billions of light years. Webb's infrared instruments allow astronomers to peer through dust and gas that would normally obscure these luminous cores, revealing how active these black holes are. The radiation doesn't just illuminate their surroundings, it can also drive powerful winds that regulate star formation, sculpt galactic structures, and even eject gas into intergalactic space. In this sense, these early monsters were not just passive observers of cosmic history, they were architects, shaping the evolution of the young universe with their immense gravitational and radiative influence. Furthermore, the discovery of these early black holes has profound implications for our understanding of dark matter and the underlying structure of the cosmos. Black holes exert gravitational forces that dominate their local environments, influencing how galaxies form and how matter clusters on large scales. If massive black holes existed earlier than expected, it suggests that the interplay between baryonic matter, the ordinary matter that makes stars and planets, and dark matter must have operated differently in the universe's infancy. The conditions that allowed these giants to form may have been seeded by dark matter halos that were denser or more massive than previously imagined, hinting at unseen forces shaping the early cosmos. Webb's observations are providing the first direct clues that such conditions may indeed have existed, forcing theorists to reconsider the very scaffolding upon which cosmic evolution builds. As Webb continued to probe the early universe, it unveiled a population of objects so peculiar that astronomers have dubbed them the little red dots. At first glance, they seem insignificant, tiny, compact points of light peppering the deep field images. But closer examination reveals that these dots are anything but ordinary. Each one represents an entire galaxy, a fully fledged collection of stars and gas, yet unlike any galaxy observed before. They are small in size, but extraordinarily bright, packing an immense amount of energy into a volume far smaller than a typical galaxy. Their luminosity hints at furious rates of star formation, creating a blindingly intense stellar output over extremely short timescales. These are galaxies burning hot and fast, ephemeral bursts of creation that shine brilliantly and then fade away, leaving only the faintest imprint in the cosmic landscape. The very existence of the little red dots challenges our notions of galactic evolution. Conventional models suggest that galaxies grow gradually, starting as small clumps of gas and dust that slowly accumulate mass over hundreds of millions of years. But the red dots tell a different story. In less than 1 billion years, some galaxies had already formed dense, energetic systems capable of producing stars at staggering rates. Webb's infrared sensitivity is crucial here, allowing us to peer through the interstellar dust that would otherwise obscure their light and reveal their true intensity. The small scale of these galaxies, combined with their extraordinary brightness, implies a mechanism of star formation far more efficient than what current theories can comfortably explain. It suggests that in the early universe, pockets of matter could collapse with incredible efficiency, forming compact, high-energy galaxies in rapid bursts rather than slow, steady accumulation. These little red dots also appear to be short-lived. Their intense star formation consumes the available gas quickly, effectively burning through their fuel and leaving behind a population of stars that will eventually cool and fade. Some may even be destroyed by feedback processes, where stellar winds and supernovae expel remaining gas, halting further star formation entirely. Webb has captured multiple examples of these fleeting galaxies at different stages, offering a kind of cinematic glimpse into the life cycle of these cosmic firecrackers. Each dot is a brief, brilliant flare in the dark canvas of the early universe, illuminating a process that may have been far more common than previously suspected, yet almost entirely invisible to earlier instruments like Hubble. The compactness of these galaxies raises additional mysteries about their structure. Unlike typical spiral or elliptical galaxies, which spread their stars over tens of thousands of light-years, these little red dots are tightly packed, sometimes just a fraction of the size of the Milky Way, yet generating luminosities rivaling much larger systems. How could such density arise without fragmenting or destabilizing under gravity? The answer may lie in the turbulent conditions of the early universe. Gravity, dark matter halos, and the intense pressure of gas flows may have conspired to compress matter into extraordinarily small volumes, creating galaxies that are as structurally unique as they are visually striking. In this sense, Webb is not just revealing objects, it is showing us entirely new modes of galaxy formation, processes that operate under extreme conditions in ways our previous theories did not predict. Beyond their physical characteristics, the little red dots may also hold the key to understanding the Rayonization era, a critical phase in cosmic history when the universe transitioned from opaque to transparent. Because these galaxies produce such enormous amounts of ultraviolet radiation, they could have contributed significantly to ionizing the surrounding hydrogen, effectively lighting up the universe for the first time. Their small size makes them difficult to detect in visible light, but Webb's infrared imaging allows astronomers to assess their impact, providing insights into how these tiny yet potent systems helped shape the evolution of the cosmos on large scales. In this sense, the red dots are not merely anomalies. They are agents of transformation, shaping the universe while remaining almost invisible to the instruments of the past. What truly captivates astronomers and enthusiasts alike is the paradox these galaxies embody. They are both diminutive and monumental, fleeting and formative, fragile yet capable of producing an extraordinary cosmic footprint. They remind us that size and importance are not always correlated in the universe, and that some of the most influential players in cosmic history may have been hidden in plain sight, too small to notice without the right tools. Webb's ability to uncover them is a testament to the transformative power of observing in the infrared, revealing that the universe has layers of complexity and activity that have gone unnoticed for billions of years. The little red dots also force a reconsideration of cosmic chronology. If these galaxies existed in such energetic states so early in the universe, then our models of galaxy formation, star formation rates, and even the distribution of matter may all require significant revision. They suggest that the early universe was a far more dynamic, varied, and even violent environment than previously imagined. A place where galaxies could flare into existence, exert influence, and fade away in the blink of a cosmic eye. Webb's discovery of these compact, hyperluminous systems underscores a larger theme emerging from its observations. The universe is faster, more complex, and far less predictable than our best theories anticipated. As astronomers were still grappling with the mysteries of the little red dots, Webb's observations unveiled yet another revelation that defied conventional wisdom. Elegant spiral galaxies appearing far earlier in cosmic history than anyone dared to expect. For decades, the formation of spiral galaxies, the graceful, pinwheel-like structures familiar from images of the Milky Way and other nearby systems, was thought to be a slow, delicate process. Models predicted that such symmetry and order required billions of years of cosmic evolution, the careful accumulation of stars, gas, and dark matter, gradually winding themselves into coherent, rotating disks. Webb, however, caught several examples of these spirals shining brightly in the young universe, less than 1 billion years after the Big Bang. Their very existence challenges the idea that the early cosmos was uniformly chaotic, replacing it instead with a vision of early elegance and structure appearing with astonishing speed. The detection of these spirals is a triumph of Webb's infrared capabilities. In the visible spectrum, the dense gas, dust, and energetic star formation of early galaxies obscure delicate features like spiral arms. Webb, sensitive to infrared light, penetrates these obfuscating clouds and reveals the underlying stellar structure with unprecedented clarity. The galaxies it captured exhibit well-defined arms curling around luminous central bulges, clear evidence that the processes responsible for stabilizing disk galaxies were already active far earlier than anticipated. These arms are not faint hints or irregular patterns. They are fully formed symmetrical structures, a level of organization previously thought impossible in such a young universe. To see them is to witness cosmic artistry, delicate patterns emerging in the midst of a universe still thought to be dominated by violent assembly and collisions. The presence of these spirals so early raises profound questions about galaxy formation. Traditionally, astronomers have understood spiral galaxies as the result of a gradual settling process. Gas and stars must cool and stabilize in a rotating disk, while gravitational interactions, mergers, and angular momentum shape the spiral arms over long timescales. Webb's discovery suggests that some galaxies found an unusually efficient way to organize themselves, assembling massive disks and establishing rotation patterns with astonishing speed. The young universe must have been capable of creating conditions conducive to rapid cooling and angular momentum alignment, a scenario that demands revisions to simulations of early galaxy formation. These spirals imply that order can emerge even amidst the turbulence of the first billion years, revealing a level of cosmic sophistication far earlier than models predicted. The implications of early spiral formation extend beyond mere aesthetics. Spiral arms are sites of active star formation, where gas clouds collapse under gravity to ignite new stars, enriching their surroundings with heavy elements. Observing these early spirals gives astronomers a window into how the first generations of stars may have been born in well-organized structures rather than chaotic bursts alone. It also raises the possibility that early galaxies may have hosted environments suitable for the formation of planets sooner than expected, though of course, these would be nascent systems far removed from habitability. Nevertheless, the existence of spiral arms at this stage indicates that the universe's capacity for creating complex, organized systems manifested remarkably early, painting a picture of a cosmos that is both violent and unexpectedly orderly. Webb's images show that these spirals often exist alongside other young galaxies, embedded within dense regions of star formation and cosmic filaments. Their surroundings reveal a tapestry of interaction and growth. Gas streams feeding into the disks, smaller galaxies potentially merging at the periphery, and stars forming in intricate patterns that echo the larger scale structure of the universe. Observing spiral galaxies in this context challenges the simplistic dichotomy of early chaos versus late order. Instead, Webb presents a universe where both can coexist. Compact, high-energy galaxies blazing with new stars, chaotic mergers reshaping the cosmic landscape, and elegant spirals silently tracing arcs of order amidst it all. The sheer elegance of these spirals also invites reflection on the processes that govern galactic evolution. To maintain spiral structure, galaxies must balance gravitational forces, rotational momentum, and the turbulent energy of star-forming regions. That these young galaxies could achieve such balance so quickly implies that the laws of physics are capable of orchestrating order on vast scales with astonishing speed. Each spiral is a testament to the universe's ability to craft structure out of chaos, demonstrating that even in its earliest epochs, cosmic evolution was not purely random, but guided by underlying forces capable of producing beauty and symmetry. Perhaps most striking is what these spirals reveal about the timeline of cosmic growth. If fully formed disks existed just 1 billion years after the Big Bang, then the processes of matter accretion, star formation, and disk stabilization must have operated on accelerated schedules. This realization has profound implications for understanding the history of galaxies, like our own Milky Way. Webb's discoveries suggest that the seeds of modern galactic architecture were planted astonishingly early, setting the stage for billions of years of evolution in a universe already capable of producing order, complexity, and elegance almost immediately. While the young universe was revealing its hidden galaxies and unexpectedly early spirals, Webb's gaze also turned to a much closer and more intimate scale, revealing a spectacle in the life cycle of a single star that challenged long-held assumptions about stellar death. The planetary nebula NGC 1514, located roughly 4,000 light-years away in the constellation Taurus, had long intrigued astronomers for its unusual structure. Hubble and ground-based telescopes had captured glimpses of its glowing outer shell, but Webb's infrared vision revealed an entirely new aspect: intricate, glowing dust rings encircling the dying star at its core. These rings were not mere symmetrical halos. They displayed turbulence, asymmetry, and unexpected density variations that defied the simplicity of classical nebula models. In essence, Webb showed that even the death throes of a single star could be far more complex and dynamic than previously imagined. NGC 1514's central star is a binary system consisting of a hot, dying star paired with a smaller companion. This duality may hold the key to the strange structures Webb revealed. The dust rings appear warped and uneven, suggesting that the interaction between the two stars sculpts the outflowing material in ways that are highly unpredictable. Gas and dust are being ejected from the dying star, but not uniformly. Instead, they form arcs, clumps, and filaments that spiral outward in patterns influenced by the companion's gravitational tug. Webb's infrared sensitivity allows it to penetrate regions opaque to visible light, exposing these dense dust lanes and revealing how matter expelled by dying stars is distributed across the surrounding space. The complexity of the rings implies that even in what might seem like a relatively straightforward phase of stellar evolution, the processes at play are chaotic, turbulent, and deeply influenced by subtle interactions between stars. The discovery also challenges our understanding of planetary nebula formation. Traditional models depict planetary nebulae as nearly spherical shells of gas and dust expelled symmetrically by aging stars, glowing under the ultraviolet radiation of the remaining stellar core. But Webb's images of NGC 1514 show that reality is far messier. The dust rings are not uniform. They are lopsided, warped, and punctuated by dense clumps that suggest episodic bursts of ejection rather than a smooth flow. This asymmetry hints at previously underappreciated forces at work, including magnetic fields, stellar winds, and the gravitational influence of the binary companion. These factors interact in ways that produce chaotic, unpredictable structures, demonstrating that even familiar objects like planetary nebula can harbor surprises when viewed in new wavelengths. Infrared observations are particularly revealing because they detect the thermal emission from dust grains warmed by the dying star's radiation. These grains, composed of silicates, carbon compounds, and other heavy elements, are the building blocks for future generations of planets and stars. In NGC 1514, Webb sees dust arranged in concentric rings, but with variations in brightness and density that indicate complex flows of matter. Some rings appear fractured or offset, suggesting that material is being expelled in bursts or redirected by shocks within the nebula. The nebula is not a static shell, but a dynamic, evolving system where matter is continuously reshaped, offering a glimpse into the chaotic physics that governs the final stages of stellar life. This discovery has implications beyond the nebula itself. Dust expelled from dying stars like NGC 1514 contributes to the interstellar medium, seeding future generations of stars and planets with the elements necessary for life. Understanding the processes that distribute dust is therefore crucial for understanding the chemical evolution of galaxies. Webb's ability to resolve fine structures within the dust rings allows astronomers to model how this material disperses over time, how turbulence affects its distribution, and how interactions with companion stars influence the shapes of planetary nebulae. Each ring, each clump of dust, becomes a puzzle piece in the larger story of cosmic recycling, demonstrating how matter ejected by a single dying star can play a role in shaping the broader galaxy. Furthermore, the asymmetry observed in NGC 1514 suggests that binary interactions may be more important in shaping nebulae than previously recognized. Many planetary nebulae were assumed to be roughly spherical, and asymmetries were often attributed to external factors like magnetic fields or collisions with surrounding gas. Webb's data show that even internal stellar companions can generate significant structural complexity. The tidal forces exerted by a companion can redirect outflows, warp expanding shells, and induce turbulence, creating the intricate, ring-like structures now visible in infrared. This realization opens new avenues for studying stellar evolution, prompting astronomers to revisit models that have long assumed simplicity in nebula morphology. NGC 1514 also provides a vivid demonstration of how different wavelengths reveal entirely new aspects of familiar objects. While optical telescopes offered a beautiful view of the glowing gas, Webb's infrared imaging uncovered the underlying dust rings and their chaotic intricacies. It is a reminder that what we see in visible light is only part of the story. The universe contains layers of structure and complexity that are invisible without the right tools. Webb's discovery here is not just a technical triumph. It fundamentally changes how we think about the death of stars, the formation of nebulae, and the cosmic life cycle of matter. The beauty of NGC 1514 lies not only in its visual spectacle, but in the profound scientific lessons it conveys. Stars, even in death, are not passive entities releasing matter uniformly. They are dynamic, interactive systems whose final outflows are shaped by physics both subtle and violent. The dust rings, with their turbulence and asymmetry, testify to forces that we are only beginning to understand. They challenge assumptions, invite new theories, and underscore a recurring theme of Webb's discoveries. The universe is far more complex, unpredictable, and magnificent than we ever imagined. While Webb unveiled the chaotic beauty of dying stars, it also turned its gaze to systems that are still very much alive, offering glimpses into the ongoing processes of planetary formation. One of the most striking examples comes from Fomalhaut, a bright nearby star long known for its peculiar circumstellar features. Previous observations hinted at the existence of a dusty debris disk surrounding the star, but Webb's unprecedented infrared clarity revealed this system in exquisite detail. The telescope uncovered multiple, crisp rings of debris encircling Fomalhaut, with striking gaps between them. These gaps are not random. They suggest the gravitational influence of unseen planets, sculpting the disk and shaping the environment in ways that were invisible until now. This discovery transforms our understanding of how planetary systems evolve, showing that even relatively mature stars can host complex, dynamically active structures. The discovery of Fomalhaut's belts exemplifies the power of Webb's infrared vision. While optical telescopes can capture scattered light from dust, infrared wavelengths detect the thermal glow of particles warmed by the star, revealing both their distribution and density. Webb's images show that the debris is not uniformly spread. Instead, it forms sharply defined rings, suggesting the presence of shepherding planets that confine material to specific orbital zones. These gaps are analogous to the divisions in Saturn's rings, where tiny moons exert gravitational forces to maintain clear boundaries. In the case of Fomalhaut, however, the scale is cosmic. We are witnessing planetary architecture on a scale measured in tens of billions of kilometers, and yet the physical processes are strikingly similar to what we observe in our own solar system. The implications of these belts are profound. Each ring represents a region where dust and small bodies, comets, asteroids, or planetesimals, are concentrated, potentially the raw material for future planet formation or the remnants of past collisions. The gaps between the rings strongly suggest that unseen planets are actively shaping the debris, their gravity carving paths through the material and maintaining the system's intricate structure. Webb's observations allow astronomers to infer the presence of these planets even without directly imaging them, providing crucial clues about their masses, orbits, and interactions with surrounding matter. The system becomes a natural laboratory for studying planetary dynamics, offering insights into how planets sculpt their environments long after their formation. Fomalhaut's belts also reveal unexpected complexity in the arrangement of debris. Unlike a single, uniform disk, the system contains multiple nested rings, each with different radii and densities. Some regions appear clumpy, suggesting collisions between planetesimals, while others remain smooth, hinting at stable zones maintained by planetary influence. This level of detail was previously unattainable. Hubble and other telescopes provided only blurry approximations of the disk, leaving much of the system's structure hidden. Webb's high-resolution infrared imaging now allows astronomers to map the belts with precision, study their composition, and understand how planets and dust interact over millions of years. The system is not static. It is alive with motion, shaped by gravity and collisions, a dynamic environment that echoes the early processes of our own solar system. The discovery of these belts also prompts questions about planetary formation timelines. Fomalhaut is a relatively young star, estimated at around 440 million years old. Yet its debris system is already highly structured, with sharp rings and gaps implying the influence of fully formed planets. This suggests that planet formation may occur more quickly and efficiently than traditional models predict, at least in some systems. Webb's observations hint at a universe where planetary architecture can emerge in hundreds of millions rather than billions of years, and where unseen worlds can exert profound influence on their surroundings long before they become directly observable. Moreover, Webb's infrared data reveals subtle asymmetries in the rings, indicating that planetary interactions are not always uniform or predictable. Some areas are denser, others more diffuse, and the orbits of potential shepherding planets may be eccentric or inclined relative to the main plane of the disk. These irregularities provide vital clues about the history of the system. Collisions, migrations, and gravitational perturbations leave measurable imprints on the debris, encoding a record of planetary dynamics over millions of years. In this sense, Webb has not merely captured a static snapshot. It has opened a window into the complex, evolving story of a planetary system still in motion. Fomalhaut's belts also offer a tantalizing glimpse into processes that may be mirrored across countless other stars. Debris disks are common around young and middle-aged stars, but the level of resolution Webb provides allows astronomers to discern details that were previously invisible. By studying the structure and composition of these rings, scientists can refine models of planetary formation and migration, understand the frequency of Earth-like and giant planets, and explore the conditions that make planetary systems stable over long timescales. Fomalhaut becomes more than a single star system. It becomes a blueprint for understanding how planets and debris interact throughout the galaxy. The elegance of Fomalhaut's rings reinforces a recurring theme emerging from Webb's observations. The universe is structured, intricate, and often unexpectedly orderly, even amid processes that appear chaotic at first glance. From wandering planet twins to early spirals and chaotic stellar deaths, Webb continues to show that cosmic evolution operates on multiple scales simultaneously, blending turbulence with grace, violence with beauty. In Fomalhaut, we see a microcosm of this interplay, a stellar system where planets, dust, and gravity choreograph a delicate dance, hidden in plain sight until Webb illuminated it with unprecedented clarity. Beyond the sculpted elegance of Fomalhaut's belts, Webb's observations reached even further into the fundamental ingredients of planets, uncovering one of the most tantalizing discoveries in recent astronomy: frozen water in the debris disk of a distant, sun-like star. Water is often described as the essence of life, and finding it outside our solar system has profound implications for the formation of habitable worlds. While water vapor had been detected in the atmospheres of some exoplanets and the icy moons within our solar system, Webb's detection of solid water in a distant debris disk represents a glimpse into the primordial stages of planetary system formation, revealing the raw materials that can seed future planets with the potential for oceans, atmospheres, and ultimately, life. The debris disk, where this frozen water resides, is a dense, swirling plain of gas, dust, and icy particles orbiting its parent star. Infrared spectroscopy allowed Webb to identify the specific spectral signatures of water ice, confirming its presence among other elements and compounds in the disk. These icy grains are likely similar in composition to the comets and asteroids of our own solar system, acting as carriers of water and organic molecules. Their detection in a sun-like system indicates that the processes responsible for delivering water to terrestrial planets may be universal, not confined to our cosmic neighborhood. Essentially, Webb is observing a stage in which the building blocks for potentially habitable worlds are assembled, billions of years before planets like Earth might fully form. What makes this discovery particularly compelling is the age of the system. It is relatively young, meaning the star and its surrounding disk are still in the process of evolving. The presence of water ice in such a young environment suggests that conditions favorable for life, or at least for the materials necessary for life, arise quickly in stellar systems. The disk contains icy grains intermixed with silicate dust, revealing a complex chemical environment. Collisions between icy bodies within the disk can redistribute water and other volatiles, a process that may mirror the delivery of water to Earth via comets in its early history. Webb's findings provide a tangible link between these primordial processes and the emergence of habitable conditions on rocky worlds, offering a window into the universality of life's chemical prerequisites. The spatial distribution of the ice is equally informative. Webb's infrared mapping shows that the water is concentrated in specific regions of the disk, likely corresponding to zones where temperatures are low enough to prevent sublimation, yet dense enough for icy particles to collide and aggregate. These cold belts are analogous to our own Kuiper belt, where icy bodies like Pluto, Haumea, and countless smaller objects reside. The presence of such zones around other stars reinforces the idea that the architecture of planetary systems, including regions rich in water ice, is a common outcome of stellar formation, hinting at the possibility that Earth-like planets with oceans may not be rare, but rather an expected product of certain cosmic environments. Webb's detection also sheds light on the processes that transport water and other volatiles inward toward terrestrial planets. In our solar system, comets and icy planetesimals are thought to have delivered much of Earth's water long after the planet formed. Observing ice in the outer regions of a debris disk suggests that similar mechanisms could operate in other systems, potentially supplying young rocky planets with essential ingredients for habitability. This reinforces the notion that life-friendly chemistry may be established even before the planets themselves are fully formed, setting the stage for environments where oceans, atmospheres, and possibly even life can arise. Another remarkable aspect of this discovery is the level of detail Webb provides about the composition of the icy particles. By analyzing subtle variations in the infrared spectrum, astronomers can infer the crystalline structure of the ice, the presence of other volatile compounds, and the size distribution of dust and ice grains. These details help reconstruct the physical and chemical conditions of the disk, revealing how water and other elements are incorporated into forming planetary systems. Understanding these conditions is crucial not only for predicting where water-rich planets might exist, but also for constraining models of planet formation, disk evolution, and the prevalence of potentially habitable worlds in the galaxy. The discovery of water ice also emphasizes the interconnectedness of cosmic processes. From the violent collisions of young galaxies to the formation of elegant spirals and the sculpting of debris disks by unseen planets, the universe is engaged in a continuous cycle of creation, destruction, and transformation. Within this vast framework, the presence of frozen water in a distant disk is a reminder that life's essential ingredients are not isolated anomalies. They are part of the natural order of cosmic evolution, woven into the fabric of planetary systems across the universe. Webb's ability to detect such delicate signals against the backdrop of space is a testament to both the telescope's sensitivity and the abundance of the building blocks of life. In essence, Webb's observation of water ice in deep space provides a glimpse into the earliest stages of planetary habitability. It connects the dots between stellar formation, disk evolution, and the eventual emergence of Earth-like planets. These icy grains are not just frozen remnants. They are harbingers of potential oceans, atmospheres, and environments capable of supporting life. For astronomers and enthusiasts alike, it is a profoundly exciting discovery, a silent, frozen promise that the universe may be far richer in habitable possibilities than we have ever dared to imagine. While the discovery of water ice revealed the raw materials for future worlds, Webb also captured a moment of planetary creation in real time, providing the first direct glimpse of a young planet actively shaping its surroundings. The telescope imaged a Saturn-mass planet embedded within a protoplanetary disk, carving out gaps and creating ripples in the surrounding gas and dust. This is not a static scene frozen in time. It is a dynamic snapshot of a planet literally in the act of formation, influencing the structure of its birth environment. For decades, theories suggested that planets would carve clear paths through disks as they formed, but Webb provides the first unambiguous visual proof of this process in action, bridging the gap between theory and observation. The planet resides within a dense rotating disk of material orbiting a young star, likely just a few million years old. Webb's infrared capabilities allow astronomers to penetrate the dust that obscures the planet in visible light, revealing both its presence and the sculpted features it has created. The disk shows concentric rings, sharp gaps, and spiral patterns, all consistent with gravitational interactions between the planet and surrounding material. As the planet orbits its star, its gravity shepherds nearby particles, clearing out a path while triggering waves of compression in the disk. These waves can influence the formation of other planets, guiding the aggregation of dust and gas, and shaping the architecture of the nascent planetary system. Observing this directly allows scientists to validate models of planetary formation that were previously constrained by indirect evidence alone. This young planet also provides critical insights into the timescales and efficiency of planet formation. Conventional models suggest that gas giants like Saturn should take tens of millions of years to acquire sufficient mass and carve out noticeable gaps in their disks. Webb's observations suggest that these processes can occur more rapidly than previously assumed, with significant structural effects visible even in relatively young systems. The clarity of the disk's rings and gaps indicates that planet-disk interactions begin early and can dominate the dynamics of a system long before planets are fully formed. This challenges our understanding of how quickly planetary systems achieve maturity and how the gravitational influence of a single planet can dictate the evolution of an entire disk. Furthermore, the observation highlights the interplay between planetary growth and disk material. The planet's presence not only clears space, but also concentrates material at the edges of its gap, potentially promoting the formation of additional planets in these high-density regions. The disk is not just a passive backdrop. It responds dynamically to the planet's gravity, creating a feedback loop that influences accretion rates, orbital stability, and even the chemical composition of emerging planets. Webb's images allow astronomers to model these interactions in unprecedented detail, offering a unique laboratory for understanding the mechanisms that govern planet formation and disk evolution. The significance of capturing a planet in this stage extends beyond a single system. It confirms that the sculpting of planetary disks is a universal process, likely occurring in countless systems across the galaxy. By directly observing the gravitational influence of a planet on its surroundings, Webb provides empirical evidence supporting decades of theoretical work on planet-disk interactions. This discovery bridges the gap between indirect signs of planet formation, such as disk gaps inferred from spectroscopy or scattered light images, and direct imaging of the planets responsible, offering an unparalleled view of the dynamics shaping young planetary systems. Webb also provides crucial information about the planet's composition and atmospheric properties. Infrared spectra reveal thermal emission and suggest the presence of a substantial gaseous envelope, consistent with a Saturn mass classification. By analyzing variations in temperature and brightness across the disk, astronomers can infer how the planet's formation affects the surrounding material, including the potential for localized heating and chemical enrichment. These insights are critical for understanding not only how planets acquire mass, but also how they influence the habitability potential of other bodies in the system, such as terrestrial planets forming in inner regions. Beyond the scientific insights, this image is a striking testament to the dynamic and violent processes underlying planetary formation. The planet's orbit is not a serene path, but a sculpting force, clearing gaps, redirecting dust, and triggering density waves that ripple through the disk. Webb has frozen a moment in this ongoing cosmic ballet, showing a process that, while common in the universe, is rarely visible in such clarity. Observing a planet actively shaping its birthplace reinforces the notion that planetary systems are not passive arrangements of matter. They are evolving, interactive, and often unpredictable structures, sculpted by gravity, motion, and time. Capturing a young planet in the act of formation illuminates a broader narrative emerging from Webb's observations. The universe is a place of constant creation and transformation. From wandering orphan worlds to the sculpted rings of Fomalhaut, from icy debris disks to planets carving their own paths, the cosmos is not static, but a dynamic laboratory where matter, energy, and gravity interact in complex, often surprising ways. Webb's ability to capture these processes directly underscores its transformative power, providing humanity with an unprecedented view of the mechanisms that have shaped not only distant exoplanets, but potentially our own solar system billions of years ago. As Webb's exploration of young planetary systems revealed the mechanics of formation, it also unveiled worlds whose very atmospheres challenge everything we thought we knew about chemistry under alien conditions. One of the most startling examples comes from WASP 107b, a gas giant so unlike any planet in our solar system that it almost seems to defy classification. Previously, astronomers expected methane to dominate its atmosphere, as would be typical for a planet of its temperature and size. Webb's high-resolution infrared spectroscopy, however, revealed a far stranger reality. An atmosphere rich in sulfur dioxide, abundant water vapor, and even clouds composed of fine silicate particles, essentially grains of sand suspended in an alien sky. This combination paints a picture of a planet that is chemically exotic, dynamically active, and fundamentally unlike anything our previous models predicted. WASP 107b is an inflated gas giant, meaning it has a larger radius than expected for its mass. This inflation results in a low-density, extended atmosphere, which allows Webb to probe the layers of gas with extraordinary clarity. The detection of sulfur dioxide is particularly surprising because it implies intense photochemical processes driven by the planet's close proximity to its star. Ultraviolet radiation and high-energy particles break down molecules and trigger complex chemical reactions, creating compounds that would be rare or unstable in cooler, more familiar environments. Alongside sulfur dioxide, the detection of water vapor indicates that even highly irradiated planets can retain significant amounts of volatile molecules, challenging assumptions about how atmospheres evolve under extreme stellar heating. Perhaps the most visually and conceptually striking aspect of WASP 107b's atmosphere is the presence of sand clouds. Composed of tiny silicate particles, these clouds are suspended high in the planet's atmosphere, carried by intense winds and turbulent circulation. The idea of sand raining from the sky is not just poetic. On WASP 107b, it is literal on a planetary scale. These clouds can alter the planet's thermal structure, reflecting and absorbing radiation in complex ways, while also shaping the appearance and spectra of the planet, as observed from afar. The interaction of such clouds with sulfur compounds and water vapor creates a dynamic chemical environment that challenges traditional models of atmospheric chemistry for gas giants, revealing the sheer variety of processes that can occur in extreme alien worlds. Webb's observations also provide insight into the broader physics of atmospheric circulation on inflated planets. WASP 107b is tidally locked, meaning the same side always faces its star, creating stark temperature contrasts between the day and night sides. These gradients drive supersonic winds and intense vertical mixing, which can loft heavy particles like silicate grains high into the upper atmosphere. The combination of photochemistry, thermal dynamics, and vertical transport creates an exotic, layered environment where chemical reactions can produce unexpected compounds, and where the planet's appearance and spectral signatures evolve continuously over time. By analyzing these signatures, astronomers can begin to reconstruct the complex interplay of physics and chemistry shaping alien atmospheres. The discovery of sulfur dioxide and silicate clouds on WASP 107b has far-reaching implications. First, it expands the known diversity of planetary atmospheres beyond the familiar compositions seen in the solar system. Second, it demonstrates that close-in gas giants, hot Jupiters, and similar worlds can harbour highly active, chemically complex environments, contrary to earlier assumptions that such planets might be relatively chemically simple due to extreme heat and stellar irradiation. Third, it suggests that exoplanet atmospheres are dynamic, not static. Molecules are created, destroyed, and transported on rapid timescales, giving rise to ever-changing chemical landscapes that challenge our ability to model them accurately. Moreover, WASP 107b underscores the importance of direct spectroscopic observations in understanding exoplanets. Before Webb, atmospheric studies relied largely on coarse models or indirect data, leaving many questions unresolved. By directly detecting specific molecules and analysing their distribution within the atmosphere, Webb allows astronomers to test and refine theories about planetary formation, atmospheric chemistry, and the influence of stellar irradiation on planetary evolution. In the case of WASP 107b, the combination of water, sulfur compounds, and sand clouds represents a set of conditions that would have seemed implausible just a few years ago, yet is now observable and quantifiable, opening the door to further discoveries on similarly extreme worlds. The presence of sand clouds, in particular, also raises fascinating questions about weather patterns on alien worlds. These particles likely condense from vapor at high altitudes, then fall slowly through the atmosphere, creating a kind of cosmic precipitation. Meanwhile, winds circulating at thousands of kilometers per hour can redistribute these grains, forming dense, shifting cloud layers that may vary from day to day. Such phenomena suggest that even gas giants, previously thought to be largely homogeneous in their atmospheric composition, can exhibit localized weather patterns and dynamic climate systems, comparable in complexity to the storms and winds we observe on Earth, but on scales and with compositions that are utterly alien. WASP 107b, therefore, is not merely a gas giant. It is a laboratory for understanding chemistry and physics under extreme conditions. Its inflated, low-density atmosphere allows molecules to persist in ways not possible on more compact planets, while its proximity to its star drives photochemical reactions that create unusual compounds. The interplay of sulfur dioxide, water vapor, and silicate clouds demonstrates that planetary atmospheres can be rich, layered, and chemically diverse, even under conditions that seem inhospitable to life. Webb has given humanity its first direct glimpse of such an environment, fundamentally expanding our understanding of what planets can be and what chemical possibilities exist beyond our solar system. Building on the revelations from WASP 107b, Webb's observations illuminate phenomena that stretch the imagination. Alien worlds where weather systems are not just extreme, but utterly alien in their mechanics and composition. Among the most dramatic of these are planets experiencing literal sand rain, planets where silicate grains, tiny mineral particles akin to terrestrial sand, condense in high-altitude clouds and fall toward the surface or deeper layers of the atmosphere. This phenomenon represents a form of precipitation unlike anything on Earth. Instead of water, frozen or liquid, the sky itself becomes a conveyor belt for inorganic particles, sculpting the planet's atmosphere and potentially influencing its thermal balance, chemical interactions, and even magnetic or electrical properties. Webb's ability to detect these sand grains in situ via infrared spectral signatures has opened an entirely new window into how exoplanetary atmospheres can behave under conditions far removed from our solar experience. The physics behind silicate rainfall on alien planets is both fascinating and extreme. On hot, inflated gas giants orbiting close to their stars, temperatures can soar high enough to vaporize silicate minerals. Once in vapor form, these particles rise into the upper atmosphere, where they encounter cooler regions, condensing into fine grains. Strong vertical winds then suspend these grains in clouds, circulating them around the planet, sometimes across thousands of kilometers. As the particles become heavier or coalesce, they begin to fall under gravity, forming sand rain. Unlike raindrops on Earth, these particles do not evaporate upon descent, but remain solid, interacting with surrounding gases and sometimes with other grains, creating complex atmospheric chemistry and layered cloud structures that evolve over time. Webb's infrared spectra can detect these clouds' composition and density, allowing astronomers to map their distribution and infer the underlying atmospheric dynamics driving the phenomenon. What makes these sand rains especially compelling is the impact they have on the broader planetary environment. The suspended silicate particles absorb and reflect stellar radiation, creating temperature gradients that influence atmospheric circulation patterns. They can also catalyze chemical reactions as the mineral surfaces interact with gases like sulfur dioxide, carbon monoxide, or water vapor. On planets like WASP 107b, where Webb has already detected sulfur compounds and water clouds coexisting with silicate particles, these sand rains contribute to an incredibly dynamic and chemically rich atmospheric system. The result is a planet whose sky is not just a passive layer of gas, but a turbulent reactive medium where mineral clouds move, collide, and precipitate in complex cycles. These alien weather systems also challenge prior models of planetary climate and atmospheric evolution. Traditional theories assumed that clouds on gas giants were primarily composed of volatile compounds like water, ammonia, or methane. The presence of solid silicate grains in clouds demonstrates that precipitation processes on exoplanets can operate under entirely different physical regimes. The grains' size distribution, density, and vertical mobility are determined by factors such as the planet's gravity, temperature gradient, and wind speeds, conditions that vary dramatically from planet to planet. Webb's observations suggest that planets with extreme irradiation or low density can host clouds that are not only exotic in composition, but also highly dynamic, with storms of sand that circulate continuously, sometimes encircling the planet or forming concentrated belts. Another striking feature of these silicate rains is their role in shaping the planet's observable characteristics. Dust and sand clouds can obscure deeper atmospheric layers, alter thermal emission patterns, and even affect the planet's reflective properties as seen from a distance. For exoplanet hunters and modelers, this creates both challenges and opportunities. On one hand, clouds of suspended silicates can mask the presence of other compounds, complicating spectroscopic analysis. On the other hand, the very existence of these grains provides clues about temperature, vertical mixing, and photochemical activity, allowing astronomers to reconstruct the planet's atmospheric dynamics with unprecedented precision. Webb's data thus serve as both a direct observation of alien precipitation and a diagnostic tool for understanding extreme exoplanetary environments. The implications extend even further when considering planetary evolution. Continuous sand precipitation can redistribute minerals across the atmosphere, creating stratified layers where chemical reactions occur at different altitudes. Over time, this may influence the overall composition of the atmosphere, affect heat transport, and even impact potential formation of hazes or secondary clouds. On planets where silicate rain is frequent, the skies may be perpetually opaque or reflective, with fine particles suspended for long periods, creating an alien version of weather cycles familiar to us on Earth, yet governed by physics and chemistry alien in every sense. These processes underscore the diversity of planetary climates in the galaxy and demonstrate that weather is not limited to familiar Earth-like rain or snow. It can take forms as exotic and dramatic as molten clouds, metallic snow, or sand showers. From an observational standpoint, detecting sand rain requires extremely sensitive instruments capable of capturing the subtle absorption and emission features of silicate particles at varying temperatures and pressures. Webb's infrared capabilities make this possible, revealing not only the composition, but also the vertical structure and dynamics of these clouds. By analyzing spectra across multiple wavelengths, astronomers can determine particle size distributions, altitude ranges, and even infrawind patterns within the atmosphere. In essence, Webb allows us to see alien weather on a microscopic and planetary scale simultaneously, turning speculative models into verifiable phenomena. These alien sand rains are a stark reminder of the universe's capacity for the unexpected. Planets once imagined as simple gas giants now emerge as worlds with entirely novel meteorologies, where gravity, radiation, chemistry, and turbulence combine to produce phenomena beyond terrestrial intuition. The skies of WASP 107b and similar exoplanets are active laboratories, testing the limits of atmospheric physics and revealing a universe where clouds can rain minerals, chemistry can be exotic, and weather can be more extreme than any storm ever witnessed on Earth. Webb's observations do more than catalogue these phenomena. They force a re-evaluation of planetary science itself, proving that nature's creativity is not bounded by our terrestrial experience. Continuing the theme of alien skies filled with sand and mineral precipitation, Webb revealed a phenomenon that stretches the imagination even further: clouds composed of actual crystals. On certain gas giants, the telescope detected pure quartz particles, microscopic gemstones, suspended high in the atmosphere. Unlike the sand rains previously observed, which consist of amorphous silicate grains, these quartz crystals are highly ordered, demonstrating that the extreme conditions of these planets can give rise to crystallization processes far above the planetary surface. The existence of such crystalline clouds transforms our understanding of exoplanetary atmospheres, revealing that chemistry and mineralogy can operate in ways entirely alien to Earth, where cloud formation is typically limited to water, ammonia, or other volatile compounds. The process by which these crystals form is both complex and extraordinary. At high altitudes, the temperature and pressure conditions within the atmosphere of an inflated gas giant can allow vaporized silicates to cool and condense into solid crystals rather than amorphous dust. This requires a delicate balance. The upper layers must be cool enough to allow crystallization while still containing sufficient supersaturated silicate vapor. The resulting quartz particles are buoyed by atmospheric currents, forming floating crystalline clouds that can drift across vast regions of the planet. Webb's infrared spectrometer was able to identify the characteristic spectral fingerprints of quartz, confirming the crystalline structure and distinguishing it from other silicate forms, a detection that was previously unimaginable. The presence of crystals in clouds has significant implications for atmospheric physics. Unlike amorphous sand grains, crystals interact with light differently. They can refract, reflect, and scatter radiation in complex patterns, influencing the planet's albedo and thermal structure. As sunlight, or starlight, passes through these crystalline clouds, it creates spectral signatures that Webb can detect, allowing astronomers to map the distribution, density, and size of the crystals. Moreover, the interaction between these crystals and other atmospheric constituents, such as sulfur dioxide or water vapor, can drive chemical reactions that further modify the planet's atmospheric composition. In this sense, crystalline clouds are not static decorations. They are active participants in the planet's meteorology and chemistry. The vertical distribution of these crystals also tells a story about atmospheric dynamics. On gas giants like WASP, 107b and similar worlds, strong convective currents and supersonic winds circulate material between layers, lofting heavy quartz particles to altitudes where they would not normally be expected. These crystals can persist for extended periods, supported by turbulent updrafts, and in some regions, they may accumulate into dense, highly reflective cloud decks. Webb's data suggests that such layers could cover substantial portions of the planetary atmosphere, creating shimmering, gem-like skies that would be visually spectacular if one could stand within them. This observation highlights the diversity and complexity of weather systems on alien worlds, extending far beyond anything seen within our solar system. The discovery of crystalline clouds also opens new avenues for understanding exoplanet formation and atmospheric evolution. The crystallization process indicates that heavy elements are present in sufficient abundance and can undergo phase transitions under extreme conditions. This provides clues about the initial composition of the planet, the accretion of material during its formation, and the subsequent vertical mixing that distributes these elements throughout the atmosphere. It also suggests that other exotic cloud types, composed of metallic compounds, sulfides, or other minerals, could exist on planets with different temperature and pressure profiles, pointing to a diversity of atmospheres that challenge conventional models of planetary chemistry. In addition to their chemical and physical significance, crystalline clouds have observable consequences for remote sensing. Quartz particles are highly reflective in certain infrared wavelengths, meaning that planets with crystalline clouds may appear brighter or exhibit unusual spectral features compared to those with only amorphous dust or conventional volatiles. Webb's ability to resolve these features allows astronomers to distinguish between different types of clouds, track atmospheric circulation, and even infer wind speeds and turbulence within the upper layers. Essentially, the presence of quartz clouds turns the planet's atmosphere into a dynamic laboratory, where crystal formation, circulation, and chemical interaction can be studied in ways previously impossible. The existence of such clouds also underscores the extremity of conditions on these alien worlds. Temperatures, pressures, and radiation levels that would be lethal to life as we know it, nonetheless allow for the formation of highly ordered mineral structures, suspended and circulated on planetary scales. This is a vivid reminder that chemistry in the cosmos is not constrained by terrestrial intuition. The universe experiments with forms, phases, and processes that can seem almost fantastical. Quartz clouds exemplify this, blending the aesthetics of gemstones with the harsh physics of a hostile, irradiated atmosphere. The detection of crystalline clouds is part of a broader pattern emerging from Webb's observations. Planets are dynamic, chemically rich, and often counterintuitive. From sand rains to sulfur dioxide atmospheres to floating gemstones, the telescope is revealing that the familiar categories of clouds, weather, and atmospheric chemistry cannot simply be extrapolated from Earth, or even from our solar system's gas giants. Each planet is a laboratory of extreme physics and chemistry, and each discovery pushes the boundaries of what we consider possible. Crystalline clouds are a dramatic example of this, demonstrating that even in the most hostile environments, nature can produce structures of remarkable order and beauty, suspended high above alien surfaces in a way that is both scientifically profound and visually awe-inspiring. While Webb has unveiled the exotic chemistry and dynamics of individual planetary atmospheres, its gaze also reached into the vast emptiness between stars, revealing a far more mysterious population: rogue planets. These are worlds untethered to any star, drifting alone through the galaxy like cosmic castaways. Webb's infrared capabilities allowed astronomers to detect dozens of such objects, some the size of Jupiter, glowing faintly from residual heat and friction, while others are smaller, colder, and almost invisible against the black canvas of space. The sheer number of these starless wanderers suggests that planets unbound from stellar systems may be far more common than previously imagined, raising profound questions about the processes that create them and the environments in which planets can exist. Rogue planets defy traditional paradigms of planetary formation. Conventional models assume that planets form within the disks of gas and dust surrounding young stars, gradually coalescing and settling into stable orbits. Yet these free-floating worlds demonstrate that planetary formation can result in outcomes far from orderly. Some may have been ejected from their original systems due to gravitational interactions with sibling planets or nearby stars, while others might have formed in isolation from collapsing gas clouds, independent of any parent star. Webb's observations hint that both scenarios may occur, expanding the potential diversity of planetary birth environments and suggesting that starless planets are not cosmic anomalies but integral components of the galaxy's architecture. Infrared detection is crucial for observing these rogue planets. Devoid of a nearby star to illuminate them, they emit very little visible light, making traditional telescopes nearly blind to their presence. Webb, however, can capture the faint thermal glow of their interiors, which persists long after formation. This allows astronomers to not only detect them, but also estimate their mass, temperature, and even composition. Some appear warm enough to have retained significant gaseous envelopes, hinting at active processes such as slow contraction or residual heat from formation, while others are colder, potentially resembling failed gas giants or super-Earths, wandering silently through the void. The telescope's ability to resolve these objects across interstellar distances transforms what was once speculative into concrete evidence of a galaxy teeming with isolated planetary bodies. The discovery of a sea of rogue planets also raises questions about their potential for hosting exotic environments. While these worlds lack the radiant energy of a star, internal heat sources, such as radioactive decay or residual formation heat, might allow for subsurface oceans or temporary atmospheres, particularly on larger, more massive objects. Some models suggest that if a rogue planet retained a thick atmosphere, greenhouse effects could trap internal heat, potentially creating niches of relative warmth beneath an icy surface. While life as we know it is unlikely under these conditions, the mere possibility stretches the imagination and broadens our understanding of what environments might be considered habitable or chemically active in the universe. Webb's observations also hint at the interactions these planets may have had with other celestial bodies. A rogue planet's ejection from a system is rarely gentle. Gravitational encounters with other planets or stars can send them careening into interstellar space at high velocities. The structural composition, rotation rate, and possible moons of these planets may carry imprints of past interactions, offering a fossilized record of violent cosmic events. By studying rogue planets, astronomers can gain insight into the chaotic processes that govern planetary system evolution, migration, and stability, learning not only about isolated worlds, but also about the systems they once called home. Moreover, the sheer prevalence of rogue planets as revealed by Webb has profound implications for galactic dynamics. Collectively, they represent a substantial, previously invisible component of the galaxy's mass budget. Their interactions with stars, molecular clouds, and even dark matter may subtly influence stellar orbits and the evolution of star clusters. While individually faint and isolated, their cumulative presence could affect the gravitational landscape of the Milky Way, a reminder that the unseen and unexpected often play critical roles in shaping cosmic structures. The diversity among these starless worlds is striking. Some appear to be gas giants, glowing from residual formation heat, while others are smaller, possibly terrestrial planets, drifting in frigid darkness. This spectrum suggests a rich population of rogue planets, each with unique characteristics shaped by their formation history and ejection processes. Webb's data also allow astronomers to assess their frequency relative to bound planets, hinting that in some regions of the galaxy, unbound planets may outnumber those attached to stars. A revelation that challenges long-standing assumptions about the organization and evolution of planetary systems. Rogue planets illustrate a theme increasingly evident in Webb's observations. The universe is not orderly. It is unpredictable, dynamic, and often defies the neat frameworks previously established. Just as Webb has revealed planets raining sand, clouds of quartz crystals, and atmospheres rich in exotic chemistry, it now shows that planets can exist entirely independent of stars, drifting through the cosmos as solitary wanderers. These discoveries expand our conception of what a planet can be, where it can exist, and how life-essential compounds may survive or fail in the harshest of cosmic environments. Webb's detection of a sea of rogue planets transforms empty space from a void into a realm filled with enigmatic, untethered worlds, each silently tracing its lonely path through the galaxy. Amid the revelations of gas giants with exotic clouds and rogue planets drifting in darkness, Webb's attention also turned to smaller, rocky worlds, particularly those orbiting red dwarf stars. One of the most striking discoveries involved TRAPPIST-1b, an Earth-sized exoplanet orbiting the closest red dwarf system to our solar system. Previously, planets in such systems were considered prime candidates for habitability due to their size and proximity to their star's habitable zone. However, Webb's infrared and spectroscopic observations suggest that TRAPPIST-1b may have been stripped nearly bare of its atmosphere, a finding that has profound implications for the potential habitability of planets orbiting red dwarfs across the galaxy. Red dwarf stars, while small and long-lived, are notoriously active. Their frequent stellar flares emit intense ultraviolet and X-ray radiation, which can erode the atmospheres of closely orbiting planets over time. Webb's sensitive instruments revealed that TRAPPIST-1b's atmosphere, if it ever possessed a substantial one, has likely been severely diminished or entirely lost. Key spectral lines that would indicate the presence of hydrogen, water vapor, or other atmospheric gases were either absent or exceedingly weak, suggesting that the planet is a barren, exposed world. This has major implications for our understanding of planetary survival around M-dwarfs, which make up the majority of stars in our galaxy, and raises questions about how many Earth-sized planets retain the essential layers needed for life in such volatile environments. The mechanisms behind atmospheric loss are multifaceted. Intense stellar radiation heats the upper layers of a planet's atmosphere, causing gases to expand and reach escape velocity, effectively boiling off the atmosphere into space. In addition, stellar winds, streams of charged particles emitted by the red dwarf, can strip lighter molecules, further accelerating atmospheric erosion. Webb's observations of TRAPPIST-1b provide empirical evidence of these processes, confirming theoretical predictions and offering an unprecedented opportunity to study the atmospheric evolution of rocky planets in extreme stellar environments. The stripping of its atmosphere is not just a minor adjustment, it fundamentally alters the planet's surface conditions, likely leaving it exposed to harsh radiation, temperature extremes, and chemical instability. Beyond the implications for habitability, the vanishing atmosphere provides insights into planetary formation and survival. The degree to which TRAPPIST-1b has been stripped may indicate the planet's original atmospheric composition, its mass, and even the initial conditions of the TRAPPIST-1 system. By comparing TRAPPIST-1b to its neighbouring planets within the same system, astronomers can study the effects of proximity to the star, magnetic fields, and planetary mass on atmospheric retention. Webb's precise measurements offer a rare opportunity to quantify these variables, helping to refine models of atmospheric escape and planetary resilience in environments far harsher than Earth's. Interestingly, the observation of TRAPPIST-1b's depleted atmosphere also highlights a broader trend. Small, rocky planets orbiting red dwarf stars may frequently face extreme challenges to habitability. While red dwarfs are numerous and long-lived, promising extended windows for potential life, their intense activity during the first few 100 million years can make it difficult for planets to maintain stable atmospheres. Webb's data suggests that, at least for TRAPPIST-1b, the window for habitable conditions may have closed early in the planet's history. This finding urges a re-evaluation of the habitability potential of similar exoplanets, particularly those in tightly packed red dwarf systems, where proximity to the host star exacerbates atmospheric loss. Despite its exposed and likely barren surface, TRAPPIST-1b remains scientifically invaluable. Studying its depleted atmosphere, or lack thereof, provides a baseline for understanding the evolutionary pathways of terrestrial planets under extreme stellar conditions. Webb's observations allow astronomers to compare worlds that have retained atmospheres to those that have lost them, offering insights into the interplay between stellar activity, planetary magnetism, and atmospheric chemistry. Even in its apparent lifelessness, TRAPPIST-1b serves as a critical case study in the limits of planetary survival and the factors that determine whether a world remains habitable over billions of years. Furthermore, the stripping of TRAPPIST-1b's atmosphere serves as a cautionary tale in the broader search for life beyond our solar system. While size, mass, and orbital distance were once considered strong indicators of potential habitability, Webb's findings show that stellar environment and atmospheric retention are equally crucial. A planet can possess Earth-like mass and radius, yet be rendered inhospitable if it cannot hold on to its protective envelope of gases. This nuanced understanding reshapes the priorities of exoplanet surveys, emphasizing the need to consider stellar activity, atmospheric composition, and planetary resilience when evaluating habitability prospects. In the grand context of Webb's discoveries, TRAPPIST-1b represents a sobering contrast to the spectacularly exotic worlds previously observed. While some planets boast sand rains, crystalline clouds, or sulfur-laden skies, TRAPPIST-1b shows that not all planets are resilient to the forces of their environment. It highlights the delicate balance required for habitability and underscores the role of host star behavior in shaping planetary destiny. Webb's ability to detect such a dramatic atmospheric depletion from light years away demonstrates both the telescope's sensitivity and the complex, often unforgiving nature of the universe. While TRAPPIST-1b showed the fragility of planetary atmospheres, Webb's observations also uncovered a subtler, more ethereal phenomenon: molecular hydrogen glowing in the cold darkness of interstellar space. For the first time, the telescope captured this faint luminescence, ignited not by nearby stars, but by cosmic rays, high-energy particles traveling across the galaxy at near-light speeds. These invisible rays, remnants of supernovae and other energetic cosmic events, interact with hydrogen molecules in dark nebulae, causing them to emit a dim glow in infrared wavelengths. Webb's ability to detect this delicate phenomenon highlights its extraordinary sensitivity and opens a new window into the chemistry and energy balance of the galaxy's most hidden regions. Molecular hydrogen is the most abundant molecule in the universe, yet it is notoriously difficult to observe in its cold, quiescent state. In the frigid interiors of dark clouds, where temperatures can drop to just a few tens of degrees above absolute zero, hydrogen emits almost no visible or infrared light under normal circumstances. Previously, astronomers had to rely on indirect methods, such as tracing the emission of other molecules like carbon monoxide, to infer the presence of hydrogen in these regions. Webb changed that by detecting the subtle infrared emissions caused when cosmic rays excite hydrogen molecules, essentially making the invisible visible. This is a groundbreaking achievement, as it allows scientists to study the distribution, density, and behavior of molecular hydrogen directly, rather than through proxies. The glow of hydrogen lit by cosmic rays is not merely a passive display. It carries important information about the physical conditions of the cloud. When cosmic rays collide with hydrogen molecules, they deposit energy, temporarily exciting the molecules and causing them to emit infrared light as they relax back to lower energy states. The intensity and distribution of this emission reveal the flux of cosmic rays penetrating the cloud, the density of hydrogen, and even the cloud's magnetic field structure, which can guide the motion of charged particles. Webb's observations therefore provide a unique tool for probing the interplay between interstellar chemistry, magnetic fields, and cosmic ray physics in regions of space that have remained largely hidden until now. This phenomenon also sheds light on the broader processes governing star formation. Dark clouds of molecular hydrogen are the birthplaces of new stars, yet much about their internal conditions has remained mysterious. By observing hydrogen glowing in response to cosmic rays, astronomers can map the distribution of matter within these clouds, identify regions of higher density, and trace the pathways through which energy and particles propagate. This information is crucial for understanding how stars condense from diffuse clouds, how turbulence is maintained, and how cosmic rays may influence the chemistry and temperature of star-forming regions. Essentially, Webb is revealing the invisible scaffolding upon which new stars, and potentially new planetary systems, are built. The discovery also emphasizes the pervasive influence of cosmic rays throughout the galaxy. Although invisible to the naked eye, these particles are constantly bombarding interstellar matter, shaping chemistry, ionizing molecules, and contributing to the heating of cold clouds. In the case of hydrogen, cosmic rays act as a spark, creating a faint but measurable glow that illuminates the darkest corners of the galaxy. This process highlights the subtle, interconnected dynamics of cosmic evolution. Energetic events like supernovae produce cosmic rays, which then travel vast distances and influence regions far removed from their origin, all while quietly shaping the raw material for future stars and planets. Webb's detection of hydrogen glowing in the dark also offers a benchmark for theoretical models of cosmic ray propagation. By measuring the brightness, spatial distribution, and spectral characteristics of the emission, astronomers can infer the energy spectrum and flux of cosmic rays in specific regions. This provides empirical constraints that were previously unavailable, allowing scientists to refine models of how cosmic rays travel, lose energy, and interact with interstellar gas. These insights are fundamental not only for understanding star formation, but also for broader astrophysical questions, such as the dynamics of galactic magnetic fields, the life cycle of cosmic rays, and the chemical evolution of the interstellar medium. Moreover, the phenomenon reveals the hidden vibrancy of regions that would otherwise appear completely dark in optical or traditional infrared observations. Dark clouds, previously thought to be inert and featureless, are in fact sites of continuous chemical and energetic activity, influenced by particles and radiation streaming across the galaxy. The hydrogen glow is a visual representation of this unseen activity, a faint but persistent reminder that even the coldest, darkest regions of space are far from static. Webb has effectively turned these cosmic shadows into laboratories for studying fundamental processes that govern the evolution of galaxies and star systems. In the grand tapestry of Webb's discoveries, hydrogen glowing under the influence of cosmic rays represents a different kind of cosmic shock, subtle, delicate, and invisible until illuminated by the telescope's extraordinary sensitivity. It complements the dramatic visual phenomena observed in planetary atmospheres, rogue worlds, and sand-laden clouds, reminding us that the universe's mysteries are not confined to the spectacular. Some of the most profound insights come from faint glows, tiny spectral signatures, and processes that quietly shape the formation of stars, planets, and ultimately, the conditions for life. Webb has made these processes visible, transforming our understanding of the interstellar medium from a dark void into a dynamic, energized, and chemically active environment. While hydrogen glowing under cosmic rays illuminated the subtle activity of dark clouds, Webb's gaze also penetrated regions of intense stellar birth, where the universe's newest stars emerge hidden beneath thick blankets of dust. Stellar nurseries like the Carina Nebula had long been studied by telescopes such as Hubble, which captured dazzling optical images of swirling gas and bright young stars. Yet much of the nebula's activity remained invisible, obscured by dense dust clouds that absorb and scatter visible light. Webb's infrared capabilities allowed astronomers to peer through this veil, revealing a population of baby stars, protostars, that had remained entirely hidden until now, transforming our understanding of star formation and the earliest stages of stellar evolution. These hidden stars are in the earliest phases of development, often still accreting material from their surrounding molecular clouds. Webb's infrared imaging uncovers them not as fully formed luminous stars, but as faint glows emerging from the dust and gas cocooning them. In these protostellar cores, gravity is steadily compressing gas and dust into dense concentrations, while heat generated by contraction and nuclear ignition begins to radiate outward. Previously, optical telescopes could only glimpse the occasional star that had already shed its natal envelope. Now, Webb captures the full spectrum of stellar infancy, from deeply embedded protostars to slightly older pre-main sequence stars, revealing a timeline of stellar evolution with unprecedented clarity. The Carina Nebula, a massive star-forming region over 7,500 light-years away, exemplifies the complexity and richness of these hidden stellar nurseries. Webb has identified clusters of protostars within dense, filamentary clouds of dust and gas, revealing that star formation is highly concentrated and occurs in bursts rather than a slow, uniform process. The telescope's sensitivity allows astronomers to resolve individual protostars within these dense regions, some only a few hundred astronomical units across, providing insight into the mass distribution, formation efficiency, and multiplicity of stars at birth. This is critical for understanding the initial mass function, the statistical distribution of stellar masses, which influences the evolution of galaxies and the prevalence of different types of stars throughout the universe. One of the most striking revelations is the sheer diversity among these hidden stars. Some are still heavily shrouded in dense dust, barely detectable in the infrared, while others are beginning to clear their surroundings, revealing outflows, jets, and nascent planetary disks. These disks, often invisible in optical wavelengths, are the birthplaces of planets, and Webb's ability to observe them directly allows scientists to study the conditions under which planetary systems form. By examining these structures, astronomers can infer the processes of accretion, angular momentum transfer, and disk evolution, shedding light on how planets like Earth may form in environments far different from our own solar system. The discovery of protostars in dust-obscured regions also highlights the dynamic interplay between young stars and their surroundings. Massive stars, once formed, emit intense ultraviolet radiation and powerful stellar winds, carving cavities in the surrounding nebula and influencing the formation of nearby stars. Webb captures these interactions in detail, showing shock fronts, ionized regions, and bow shocks where outflows from newborn stars collide with the surrounding medium. This dynamic feedback regulates the pace of star formation, triggering new births in some regions while halting it in others, and Webb's observations provide the clearest view yet of these complex processes in action. Additionally, the ability to detect these hidden stars provides critical information about stellar lifetimes and evolution. By observing stars at multiple stages of formation within the same region, astronomers can construct detailed evolutionary models, tracking how a dense core of gas transforms into a luminous main sequence star. Webb's observations of embedded protostars also reveal temperature gradients, chemical abundances, and dust composition within the birth clouds, offering clues about the initial conditions that will shape both stars and any planets that may form in orbit around them. These data challenge and refine previous theoretical models, which often relied on assumptions due to the lack of direct observation in heavily obscured regions. The Carina Nebula is just one example. Webb has begun to uncover similar hidden stellar populations across numerous star-forming regions, indicating that the universe is far more prolific in its creation of stars than previously appreciated. Many stars in the Milky Way may be forming in such obscured environments, invisible to traditional telescopes, but revealed by Webb's infrared vision. This suggests that our previous estimates of star formation rates may have been significantly underestimated, with profound implications for models of galactic evolution, the enrichment of interstellar matter, and the distribution of potential planetary systems. Webb's discovery of these hidden stars also underscores the importance of multi-wavelength astronomy. While optical telescopes provide breathtaking images of illuminated nebulae, they cannot penetrate dense dust. Radio observations can probe cold molecular gas, but with limited resolution for individual protostars. Infrared observations, like those from Webb, fill this critical gap, revealing both the stars themselves and the structure of their dusty envelopes. This holistic approach allows astronomers to study the full life cycle of stars, from the initial collapse of a molecular cloud to the clearing of the dust and the emergence of a young stellar object, providing a complete narrative of star formation that was previously unattainable. In observing these hidden stellar nurseries, Webb has effectively lifted the veil on the universe's most intimate and formative processes. Baby stars, once invisible in the densest, darkest clouds, now shine in the infrared spectrum, offering clues about how stars like our Sun, and potentially life-bearing planets, come into existence. The telescope reveals that star formation is neither simple nor uniform, but a complex, dynamic, and often chaotic process, influenced by turbulence, radiation, and chemical interactions at every scale. In doing so, Webb has transformed what were once shadowy, mysterious regions into active laboratories for understanding the origins of stars, planets, and ultimately, the conditions that make life possible. While Webb has unveiled the hidden births of stars in dusty nebulae, its gaze also extended to the outer reaches of our own solar system, revealing mysteries much closer to home, yet no less shocking. Makemake, a distant dwarf planet orbiting far beyond Pluto, had long been considered a frozen, inert world, a remnant of the early solar system, quietly drifting in the Kuiper belt. However, Webb's infrared observations detected something unexpected. Makemake exhibited a subtle but measurable glow, an apparent warmth that contradicted its presumed frigid surface temperatures. This anomaly has sparked speculation about possible cryovolcanic activity, residual internal heat, or even the presence of a hidden ring system, reshaping our understanding of small, icy bodies at the solar system's edge. The glow itself is faint yet significant. Infrared measurements revealed that certain regions of Makemake emit more heat than can be accounted for by sunlight alone. For a world located nearly 50 astronomical units from the Sun, where surface temperatures hover near -240 degrees Celsius, any detectable heat anomaly is extraordinary. One possibility is cryovolcanism, geological activity in which subsurface ices, including water, nitrogen, or methane, are expelled through vents onto the surface. Such eruptions would release internal energy, warming localized regions and leaving signatures detectable in infrared. Cryovolcanism has been observed or suspected on other distant icy bodies, such as Enceladus and Triton, but finding it on Makemake would indicate that even remote, small dwarf planets can remain geologically active long after formation. Another intriguing hypothesis for the mysterious warmth is a hidden ring system. Infrared data suggests that portions of Makemake's glow could be due to material orbiting the planet, composed of fine dust, ice particles, or small satellite fragments, reflecting and re-emitting heat. Rings around small outer solar system objects are rare but not unprecedented. Chariklo and Haumea both possess ring systems, demonstrating that such structures can persist even around modestly sized bodies. If Makemake indeed hosts a ring, it could explain not only the infrared emission, but also subtle photometric anomalies observed in past stellar occultations. Webb's sensitivity allows astronomers to detect these faint signatures, revealing structures that would have gone unnoticed by previous telescopes. The presence of internal heat, whether through cryovolcanism or other mechanisms, also raises questions about Makemake's composition and evolutionary history. For a small body in the Kuiper belt to retain significant internal energy over billions of years, it must either have a high concentration of radioactive elements or experience ongoing processes that generate heat. Tidal interactions with potential moons could contribute, although Makemake's known satellites are small and distant. Alternatively, slow differentiation of internal materials, chemical reactions within the ice, or even latent heat from formation could maintain a modest thermal output, sufficient to create localized warmth detectable by Webb. Makemake's glow also impacts our understanding of surface processes and atmospheric potential. Though thin and transient, sublimation of ices due to internal heating could create temporary, localized atmospheres or plumes, redistributing material across the surface. Such activity might account for subtle albedo variations and compositional heterogeneity observed in earlier optical and thermal studies. The detection of warmth by Webb provides the first direct evidence that Makemake is not a completely inert ice ball, but may harbor dynamic processes capable of reshaping its surface over time. Furthermore, the mysterious glow emphasizes the broader significance of studying distant Kuiper belt objects. These small frozen worlds are relics of the early solar system, preserving primordial materials while also undergoing slow evolution driven by internal heat, radiation, and collisions. Webb's observations reveal that even these remote bodies can surprise us, exhibiting behaviors previously thought impossible for such small, cold objects. By understanding Makemake, astronomers gain insight into the diversity of dwarf planets, the prevalence of cryovolcanism, and the potential for hidden structures like rings, which in turn informs models of solar system formation and evolution. The observation of Makemake also invites comparison with other icy bodies in the outer solar system. While Pluto and Triton exhibit complex geology and signs of past or ongoing activity, Makemake was long assumed to be relatively static. Webb's data challenge this assumption, suggesting that internal energy and dynamic processes may be more common among distant dwarf planets than previously believed. This underscores a recurring theme in Webb's discoveries. Even seemingly simple or static worlds can harbor surprises that defy expectations, reminding us that our solar system is as rich in complexity as the exoplanetary systems Webb studies beyond our neighborhood. Beyond the icy edges of our own solar system, Webb's gaze stretches into alien atmospheres, revealing chemical processes far removed from earthly experience. One of its most groundbreaking discoveries was the first definitive detection of carbon dioxide in the atmosphere of an exoplanet. While carbon dioxide is familiar to us as a greenhouse gas shaping Earth's climate, observing it light years away in a distant world's atmosphere opens an entirely new window into planetary chemistry and climate systems in environments that are utterly alien. This detection is not only a technical achievement, it provides direct insight into the composition, dynamics, and potential habitability of worlds orbiting other stars. The exoplanet in question is a gas giant, yet the principles illuminated by this discovery extend to smaller, rocky planets as well. Webb's spectroscopic instruments captured the characteristic absorption lines of CO2, allowing astronomers to confirm its presence unequivocally. This is a feat that could not have been achieved by previous telescopes, as the spectral signatures of carbon dioxide are faint and easily masked by other molecules such as water vapor or methane. By carefully analyzing the infrared light filtering through the planet's atmosphere as it transited its star, Webb disentangled the complex chemical signatures, revealing an atmosphere shaped by processes both familiar and exotic. The presence of carbon dioxide provides important clues about the planet's formation and evolution. CO2 can originate from primordial gases captured during formation, outgassing from internal processes, or chemical reactions in the atmosphere triggered by ultraviolet radiation from the host star. Webb's data suggest that all three mechanisms may contribute, depending on the altitude and temperature of the atmospheric layer being observed. This complex interplay highlights the rich chemical diversity possible in exoplanetary atmospheres, demonstrating that even a gas giant can host an active chemical environment where molecules are produced, destroyed, and redistributed in ways that challenge terrestrial intuition. Carbon dioxide also plays a critical role in the planet's energy balance. As a greenhouse gas, CO2 absorbs infrared radiation and traps heat, influencing atmospheric temperatures and dynamics. On this exoplanet, Webb's measurements reveal temperature gradients that correlate with the concentration of CO2, suggesting that the molecule significantly shapes wind patterns, thermal circulation, and perhaps even cloud formation. This is particularly intriguing because it shows that the physical and chemical principles governing atmospheres, radiative transfer, convection, molecular absorption, apply universally, yet can produce wildly different outcomes depending on the planetary environment, stellar radiation, and atmospheric composition. The discovery of CO2 also expands the potential for studying exotic chemistry. Its presence provides a baseline for identifying other carbon-bearing molecules, including carbon monoxide, methane, or more complex organic compounds. By mapping the relative abundances of these molecules, astronomers can reconstruct chemical pathways occurring in alien atmospheres, providing insight into planetary evolution, photochemistry, and even potential biosignatures. While the detection of CO2 alone does not imply life, it establishes a crucial reference point for future studies seeking to understand the chemical inventory of habitable or uninhabitable worlds. Webb's detection also demonstrates the diversity of exoplanetary atmospheres. In our solar system, CO2 is abundant on Venus and Mars, but plays very different roles on each world. Observing it on a distant gas giant suggests that the molecule's presence is not limited to terrestrial planets, but can occur under a wide range of conditions, from extreme temperatures to unusual atmospheric pressures. This diversity challenges prior assumptions that planetary atmospheres conform to predictable patterns and underscores the need to study each exoplanet as a unique laboratory of physics and chemistry. Moreover, the detection of carbon dioxide highlights Webb's unprecedented sensitivity and precision. The telescope can discern minute variations in spectral lines, revealing molecular abundances at levels previously inaccessible. This capability transforms exoplanet science from broad characterization to detailed chemical analysis, allowing researchers to explore the atmospheric composition, temperature structure, and even weather patterns of worlds many light years away. CO2 becomes more than a molecule. It is a diagnostic tool for probing the physical processes shaping alien atmospheres and the evolutionary history of these distant planets. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.